So now when you have a point anywhere in the coordinate plane, you can make a position vector. And a position vector is a vector with that point and the origin. So we usually call the origin O. So if we have a point P, O to P would be its position vector. And that way you could find any point in the coordinate plane by saying its vector, which is sort of the same idea as saying any point by its point. But we're doing vectors now, so this is going to be helpful for vectors. So as far as a vector goes, we denote it as P. So if you were writing it, you would write it with P with an arrow over top of it because you couldn't do a bold P. But that is our position vector. So what we're going to do here is we're going to sketch the position vector passing through the point -6, 5 and write it in two different ways. So as far as the picture, we go to that point, -6, 5, and all we do is draw a vector going to that point. One way that you could write that is with your unit vectors. So you go -6i plus 5j. Or you could write it as a column vector. So that's all it says here at the bottom. You can write it as a column vector or with the unit vectors I and j. So if we have two vectors, or 2 points, 1, 3, and 4, 5, we could draw their position vectors. So we have that here. A is the blue one, the position vector for A, and for point B, the green vector. And if you like, if you'd rather draw your arrowheads on the end of your vectors, you can do that as well, but sometimes that is hard to see because the arrowheads end up at the same place. But it's not wrong if you draw your arrowheads at the end of the vector. So then from going from A to B, notice that going from A to B, we go 3 to the right and 2 up. That's part of the red one. So if we put a red around that, we can see that. Now, to go to A to B, we could do that, and this is one of the key concepts of vectors. To go from A to B, we could go there directly. This is your house, right? This is your friend Bob's house. There's nothing in the way. You live out in the middle of the prairies, and if you want to, you can go directly there. Now, if you wanted to, at the origin there's a grocery store which sells bags of chips, and you think, oh, maybe it would be nice to bring a bag of chips to Bob's house. You could, if you wanted to go to Bob's house, first go to the grocery store, and since the prairies, you could walk directly there, and then walk directly to Bob's house. And you live in this utopia society where those are the only 3 buildings there are. Utopian, yes. And all the corner store sells is chips. So that would be another way to get from A to B. So we can write that as an equation, which we can write like this. I can go from A to B by first starting at A, going to O, and then from O going to B. And as far as vectors are concerned, both of them had the same starting place. Both of them had the same ending place. Vectors aren't necessarily concerned about how long it took you to get there, or whether you got chips and what kind of flavor they are. But this is going to be very helpful for us because if we have A and B, if we have position vectors, we can now find out what the resultant vector is of all sorts of vectors. You want to go from A to B, we can find that out quickly. So the idea is this. We have vectors A and B. So going to A, that's, if we label that as vector A, and going to B, we label that as vector B. Does it make sense that to go from A to B, and I personally like to write it this way because it makes sense to me. I'm starting at A. I need to go the opposite direction to get to O. That's going to be negative A. Because if A is the vector from O to A, then negative A would be the vector from A to O. Once I do negative A, now to get to B, I just have to add vector B to that. Now, it's almost always written in textbooks as B minus A because it feels better to start with the positive value. But mentally thinking about it, if you're drawing a picture, it makes more sense to do negative A first and then go to the grocery store. Technically, when I write B minus A, if I was walking in the prairies, this is what it would look like. I'm at A. I go in the direction of B, which looks like this. And then I go minus A after that, and I get back to B. The only problem here is if I did that, I wouldn't get any bags of chips, right? Because I missed the grocery store. And since this world just has those three buildings, you would get to some random spot in the prairie with nothing there and have to walk back. This is a huge idea that's really simple to visualize, okay? So all sorts of times, if you wanted to go from this point to this point, if you know what those points are, you're going to go back to the origin and then to that point. And it's always going to be negative the first vector plus the second vector. So this is the general idea. And again, it's not wrong. If you always want to write it like this. So if we write vector B, and then you subtract vector A, all you have to do is subtract the corresponding coordinates, and what we've got is a vector from A to B. So some of the reasoning behind this as we're going through this, because right now the math is not very hard, you're going to find out that there's a lot of coordinate geometry questions that you can solve quite easily using the math that we're going to develop in vectors. Even easier than if you had used your old math of finding the distance between 2 points and stuff like that. And the really nice thing about vectors is it works really, really nice also in 3 dimensions. Whereas if you had to go back to your old coordinate geometry for 3 dimensions, it would just be time consuming and a little bit frustrating. So B to A, of course, would be exactly the opposite. Because B to A is the negative of A to B, so we just take our first vector and multiply it by negative. No problem. So here we have a picture of a triangle, and it's saying if you have PQ and PR, then you could also find Q to R. Again, this is how I would think about it. I want to find Q to R. That's my resultant. What am I going to have to do? I'm going to have to go from Q to P first. And then I'm going to have to go from P to R. Now I would probably write this Q to P is negative P to Q plus P to R. But again, in most formulas, they're going to write the subtract 1 second. So there's x to the y, and there's x to z. You want to find the vectors y to z and z to y. Drawing a picture is going to be very helpful, even if you just draw that in 2 dimensions. So what do I know? I know what x to y is, I know what x to z is, and I want to find y to z and z to y. Well, if I want to find y to z, I'm going to start at y, and I need to end at z. Can you see that you're going to need to do this one negative, and then this one the same as it was before? So from y to z, you're going to go y to x, and then x to z. And that's going to get you at the same place. But y to x is just the same as negative xy. So here we got negative 5, 4, negative 5, negative 4, 3, and then add x to z. So you find out that it's 5, negative 4, 5. And of course, z to y would just be the opposite of that. So you'd have all the negatives there. Yes? 10, 0, negative. Thank you. And then this will be a 1. So again, the picture is really helpful because it tells you what you need to do. Okay? Something also for adding vectors if you didn't want to draw the picture. Notice that when you're adding vectors together, if these coordinates are the same, when you're adding 2 in a row, this means I'm going from y to x, and now I'm at x. And this means I'm starting at x and going to z. So if I go from y to x and then from x to z, I'm going to end up at y to z. And so you can get that idea from that as well if you don't want to draw the picture. But drawing the picture doesn't take very long, and it makes all of the visuals really easy to see. That you need to go from y to x and then x to z. So we've got 3 position vectors, A, B, and C, in 3 dimensions. And we want to show that these 3 points are all in a straight line. So now we think back to our coordinate geometry from what we did before. From what we would have done before, now you're imagining 3 points in 3 dimensions, and you're trying to say that that lines up perfectly in a straight line. So just the visualization of how you would do this with the mathematics that we had before, you can see that it might be quite difficult. This is the idea. This is what we want to show. Well, there's a couple of ways that we can show this. Any ideas? The slopes, we have to put slopes in quotation marks with 3 fingers because it's 3-dimensional. The slopes, if the slopes are the same, then you would know they're going in the same direction, and that would make them in a same line. Good. Another thing you could do is you could look at the distances. Right? If the distance from A to B plus the distance from B to C is equal to the distance from A to C, then it has to be a straight line as well. Oh, I see what you're saying. Yeah, well, we would figure out the distance from A to B, B to C, and A to C, and figure out which distance was in the middle. Yes, but that does make the assumption from our picture here that B is in the middle. So, the vector from A to B is, in its sense, its direction vector, it's its slope. So going from A to B is 1, 3, negative 2. And going from B to C is going to be 3, 9, negative 6. So are those slopes the same? Well, we can go back to our ideas before and say, well, if two things are parallel, then one is a multiple of the other one. And here you can see that AB times 3 is equal to BC. Or in other words, you could factor out a 3 out of this one and get 1, 3, negative 2. And since they share a point and they have the same direction or same slope, these would have to be in the same line. If you wanted to do the distance method, that's just finding the magnitude. So if we were finding the magnitude of this one, A to B, we would have 1 squared plus 3 squared plus negative 2 squared, square root of 14. And if we would find the distance between B to C, it's going to be, well, because we can factor out that 3, we can do it that way, 3 times root 14. Or we could have done 9 plus 81 plus 36, which is 126, which if you divide that by 9, you get 14 anyways. So it's going to be 3 root 14. And if you figured out from A to C, that vector is going to be 4, 12, negative 8, which is 4 times 1, 3, and negative 2. Its length, the length from A to C, is going to be 4 root 14. So if you have A to B is root 14, and B to C is 3 root 14, adding them together, you'll get 4 root 14. And since they share a common point, they would have to be in a straight line for that reason as well. So I'll let you try this one. I'll put the answer up in a second.